welcome to Virtual Protocol Podcast.
You know, it's a slightly unsettling thought, but while you were sleeping this past week, artificial intelligence definitely was not.
No, it really wasn't taking any breaks.
Right. I mean, while you were catching those Zs, AI was busy composing full orchestral symphonies, predicting the exact path of future hurricanes, and casually solving decades-old math problems that no human being has ever been able to crack.
It has been an incredibly busy week.
Yeah, we've got our hands on this really dense rapid-fire update covering the absolute latest in AI news and tool releases. But instead of just reading down a grocery list of software updates to you, we're going to cut through that massive volume of noise and connect the dots.
Because there's a very clear pattern emerging here.
Exactly. Our mission for this deep dive is to show you how we are firmly moving away from the era of AI as just a simple chatbot that you type a query into. We are entering this wild new era of multi-agent orchestration and entirely autonomous scientific discovery.
The shift is fundamental. I mean, what is truly fascinating here isn't just the sheer number of new models dropping every week, but how these systems are starting to interact with the physical world.
Yeah.
And more importantly, they are learning to manage their own complex workflows over extended periods of time, completely without any humans steering the ship.
Which is mind-blowing. And to really understand how AI is learning to manage multiple complex variables at once, we can actually look at the arts, of all things. It's become the first real proving ground for this kind of complex management.
It really has.
Like, take SymphonyGen, for example. This is a new open-source AI that generates full orchestral music. But the wild part is the footprint. The model itself is under 5 megabytes. You could fit this thing on a 2-decade-old thumb drive.
Right, which completely defies our traditional expectations of file size and model complexity.
How does it even do that? 5 megabytes is nothing.
Well, the reason it achieves that efficiency comes down to how it handles coordination. The AI isn't holding massive, uncompressed audio files of cellos and trumpets in its memory. Instead, it generates what they call a harmony skeleton.
A harmony skeleton.
Yeah, it creates a mathematical framework of chords and pacing first. And then it expands that basic outline into a complete arrangement, synthesizing the instrument's sounds procedurally.
It kind of makes me think of a musical coloring book. Like you, the human, draw the bold black lines, the
Right.
chords, the basic direction, and the AI acts like a team of artists coming in and coloring in the specific instruments, the violins, the brass, perfectly within those lines.
That is a perfect analogy. That structural approach, establishing the macro framework before filling in the micro details, is essentially how these models handle complex timing.
Yeah, and we see a really similar mechanism in vocal generation now, right? With Vocal Render and its upgraded version, Vocal Render Pro.
Yes, those models generate incredibly realistic singing voices from just text lyrics and MIDI notes, and they easily outperform competitors like Vivo 2.
Oh man, I saw those Vivo 2 examples, and they definitely would not make it past the audition round of a talent show. I mean, it struggles to even adhere to the specified pitch.
It does, but vocal render is fascinating.
Yeah, the mechanics behind it are what I want to dig into. Because how does it get the timing so perfect? Especially when, one sung syllable needs to stretch and bend across multiple different musical notes.
So it relies on a two-step process that separates the timing from the actual sound. Under the hood, it first uses an autoregressive model,
Okay.
which you can think of kind of like predictive text on your phone, but for musical rhythm. It predicts the next logical step in a sequence to build a broad, rough sketch of the singing style and how long a syllable should last.
Got it. So it gets the timing down first.
Exactly. And once that foundation is set, the fusion model takes over. Diffusion works by starting with pure static noise and slowly carving away that noise until a highly detailed audio wave is left.
Like sculpting it.
Yes, it sculpts the exact pitch, the vocal tone, the breathiness, fitting it perfectly into the timing framework that the first model built.
That dual model coordination is so cool. And it's jumping over to visual arts too. We have One Animate 2, which animates still images using reference videos.
And it transfers hand movements and facial expressions accurately.
Yeah, and it even works on irregular body proportions. Like you can animate a teddy bear with it or handle multiple characters at once. The full version is a massive 33 gigabytes, but they released this light in-8 version that allows for real-time streaming with less than a second of latency.
That in-8 designation is really the key to the speed there.
What does that mean exactly?
It stands for 8-bit integer format. Normally, AI models use highly precise, memory-heavy floating point math to calculate their outputs. But by compressing the model down to 8-bit integers, they sacrifice just a tiny fraction of microscopic precision.
But I'm guessing the trade-off is worth it.
Oh, absolutely. The math becomes so lightweight that the processing speed skyrockets. That is how they achieve latency under 1 second, clearing a huge technical hurdle for live video generation.
That makes a lot of sense. I mean, you don't need decimal point precision for a live stream avatar. You just need it to be fast.
Exactly.
And speaking of manipulating visuals, Tencent just released Hunyuan 3D Buffalo.
Yes, that's a very powerful tool.
It is a unified model that can generate, edit, and segment 3D objects. And by segmenting, I mean it actually understands the geometry well enough to isolate specific parts. You can ask it to add glasses to a 3D model of a frog, and it knows exactly where the bridge at the nose is.
Or you can ask it to attach spiked gauntlets to a robot, and it just knows how to connect them.
Right. And then over in video generation, Higgsfield's Seance 2.5 takes this synthesis even further. It generates up to 30 seconds of video by combining up to 50 different references.
It's a massive amount of input.
Yeah, you can feed it static images, audio tracks, even 3D clay renders, and it just orchestrates all of them on a timeline for exact timestamp-specific editing.
The underlying trend connecting one animate, Hunyuan, and Seance is unified orchestration. Like just a year ago, you would need one AI to build a 3D model, a completely different AI to isolate its parts, and a third to animate it.
Yeah, it was super disjointed.
Exactly. But now, the AI is learning to orchestrate all these different independent data types simultaneously to create a cohesive output.
Okay, I do want to push back on one of the visual tools that attempts this orchestration, though, and that's Leap Talk.
Ah, yes.
So this model generates talking avatars from a photo and an audio clip. The big claim is that it can run at a staggering 200 frames per second on an H200 GPU.
Which is insanely fast.
It is, and I know the H200 is this top-tier piece of hardware with massive memory bandwidth designed for real-time inference, which explains the raw speed. But when you actually look at the output, the avatar is incredibly rigid.
It does have a certain stiffness to it.
It looks like a robotic puppet compared to some of the slower, more expressive models. Is that raw speed really worth the trade-off of looking so unnatural?
Well, the value of that trade-off entirely depends on the application. Yeah. For a high-end film production or a marketing campaign, Leap Talk would be the wrong choice because visual fidelity is paramount.
Right.
But consider a real-time interactive customer service agent or a live translation avatar for a video call. In those scenarios, if there's a 2-second delay before the avatar moves its lips, the interaction just feels broken.
Oh, that makes sense. It ruins the illusion of a conversation.
Exactly. When latency has to be near zero, 200 frames per second is a vital capability. Whether it is timing a stretched syllable in vocal render or syncing lips instantly in Leap Talk, the core capability being mastered is real-time complex coordination.
Okay, so if an AI can coordinate a symphony of digital instruments and visual references, I guess the next logical hurdle is coordinating physical, real-world variables.
And we are seeing that bridge being built right now.
Yeah, let's look at MASC, which stands for Multi-Agent CAD. This tool turns text prompts into 3D printable CAD models. It is 10 times cheaper and uses 116 times fewer tokens than older models like CAD skills, and it achieves a much higher pass rate.
Using 116 times fewer tokens is a dramatic leap in efficiency.
And a token here is just a unit of data, right?
Basically, yes.
Yep.
It's a unit of data the AI uses to map 3D space. By requiring significantly fewer tokens to process the geometry, the computational cost just plummets, meaning the barrier to physical manufacturing and rapid prototyping drops significantly.
But orchestration in the physical world is going far beyond just 3D printing brackets and gears. Google DeepMind just open-sourced weather next to.
This one is fascinating.
It really is. It combines storm track and storm intensity predictions into one single model. It can predict hurricanes up to 15 days out by running an ensemble of 1,000 different possible scenarios.
And they released a mini version for Google Colab, too.
Right. But what really caught my attention is the data resolution. Weather Next 2 uses 28 by 28 kilometer resolution, which is 100 times coarser than traditional weather models.
Yes, much lower resolution.
And because it uses this chunkier data, it can run a full 15-day forecast in under a minute on a single Google TPU, their custom hardware for this kind of math. But this feels completely counterintuitive to me.
How so?
It's like trying to navigate using a blurred map. How does using coarser, lower resolution data actually make the AI faster and more accurate than traditional models that use ultra-high resolution data?
I get why that seems backwards. We intuitively assume that more detail always equals better prediction, especially with weather. But highly detailed data can actually cause AI models to overcorrect.
Really?
Yeah. If a traditional model is looking at ultra-high resolution data, it might get distracted by a single anomalous cloud formation or localized temperature spike. And that leads to a phenomenon where the AI essentially hallucinates a storm that won't happen.
Oh.
Google trained WeatherNext 2 on nearly 20 terabytes of global atmospheric data, including 5,000 historical storms. By forcing the AI to look at a 28-kilometer grid,
That blurred map.
exactly, the blurred map, it physically cannot get bogged down in microscopic localized details. It is forced to focus on the massive, sweeping atmospheric currents and macro pressure systems. Because it ignores the localized noise, it doesn't overcorrect, allowing it to rapidly simulate 1,000 possible futures with incredible accuracy.
Okay, that paints a really clear picture. It literally forces the AI to see the forest instead of getting lost inspecting a single tree.
Exactly.
And that same principle of synthesizing macro patterns is showing up in medicine too, with Alibaba's ClinFusion.
Yes.
This is an open source model that understands both 2D and 3D medical data, like traditional X-rays combined with full MRI scans, all in one system to generate clinical reports.
Synthesizing completely different types of physical data into a single diagnostic understanding.
Right, and it actually beats proprietary models like GPT 5.2. Plus, it comes in a 32 billion parameter size and an 8 billion parameter size, meaning hospitals can run it locally on standard hardware without sending patient data to the cloud.
Bringing that synthesis into local environments is critical for medical privacy. But the underlying achievement really is the multimodal understanding. The AI is proving it can navigate the physical realities of the human body across different dimensions of imaging.
And navigating physical reality brings us straight to the robotics updates, which are just accelerating at a crazy pace.
The real-world applications are expanding so quickly.
For sure. Persona AI demonstrated a VR teleoperation system where a human remotely controls a humanoid robot to do high-risk industrial welding. UB Robotics previewed their Cruiser Y1, which uses swarm intelligence.
Right. An entire army of wheeled humanoid robots coordinating together in a warehouse without any overlap.
Yeah, but the one that really stood out to me was Xiaomi's new foundation model, Robotics 1. The demo showed it doing highly dexterous tasks like zipping bags and packing suitcases.
Very fine motor control.
Yeah, and the training method is what fascinates me here. Xiaomi collected 100,000 hours of video just by having human beings walk around their homes and factories carrying a handheld gripper with a camera attached to it.
Just walking around gathering POV data.
Right. They trained the AI on that human data first, and then adapted it to the actual robot body using only 10,000 hours of real robot data. My immediate thought is that they are trying to bypass the hardest part of robotics, which is basic physics.
Yes.
Like, humans already know how gravity works, how much friction is needed to hold a cup, how to pull a zipper without snapping it. So they're just teaching the AI the physics of the world first, rather than trying to teach a robot body from scratch.
That is precisely the strategy. It connects directly back to the WeatherNext 2 principle of macro patterns we just talked about.
Oh, how so?
Well, learning the overarching physics of the world, how objects feel, how they interact, spatial awareness, that is the most computationally expensive part of training a physical agent. By utilizing a handheld gripper, the AI absorbs those generalized manipulation skills from human intuition.
Oh, I see.
Once it masters the physics of the environment, adapting those general rules to the specific joints and motors of a robot body is just a matter of fine-tuning. It drastically reduces the time and cost of deployment.
That is so smart. But, predicting physical weather patterns and navigating living rooms is one thing. If AI can synthesize physical reality the next step is setting it loose on abstract intellectual problems. We are really looking at the dawn of unsupervised thinkers.
This is where the paradigm shift moves from mere automation to the actual generation of knowledge.
Yeah. So Alibaba recently open-sourced Qwen 3.8 Max, which is a massive 2.4 trillion parameter model. And in one experiment, researchers gave this AI an empty folder and told it to build a self-improving GitHub harness.
And it did it entirely on its own.
Right. The AI ran autonomously for 16 days. It generated code, tested it, found its own errors, rewrote the code, and deployed it, all without a single human prompt. It made 265 commits and 127 pull requests.
Incredible persistence.
And in another test, it was handed a recent AI paper and told to reproduce it and beat it. Over 5 days, it wrote thousands of lines of code, invented 18 of its own unique improvements, and beat the original paper's result by 2.7 points. It even designed and optimized a cryptographic chip layout to be 12 times smaller than the baseline.
The implication here is profound. The AI is no longer just functioning as a tool for the scientist. The AI is functioning as the scientist.
Yeah.
It is iterating on hypotheses completely independently.
We see that autonomous iteration pushed even further with this experimental model called Big Bang. It's built on a much smaller model, Kin 3.635b, but it uses this self-evolving framework.
The agent interaction Big Bang is very interesting.
Yeah, it works by having generator agents create really hard scientific problems, critic agents reject the weak ones, and metacritics test the AI on real research. Just by looping this process over and over, its score on the frontier science benchmark jumped from 12 points to 46 points.
A massive leap.
It is, but I have to stop here and push back on the premise a bit.
Okay.
Logically, if an AI is just talking to itself, pulling knowledge out of thin air, doesn't the synthetic data loop eventually have to hit a hard ceiling? Like a closed loop can't invent entirely novel data forever without hitting an intelligence wall, right?
That is a very astute critique of synthetic data. Honestly, calling it a self-evolving model is a highly optimistic marketing term for what is essentially an automated synthetic data pipeline.
Right, that's what I thought.
You are correct that a completely closed loop will eventually hit a ceiling of diminishing returns. However, the mechanism of having specialized agents challenge each other forces the model to refine its logical pathways, even if it isn't ingesting new external facts.
Yeah, it gets better at thinking, basically.
Exactly. And when we look at the absolute frontier of these unsupervised models, they are absolutely breaking through established ceilings. Just look at the recent developments surrounding OpenAI's internal model, codenamed Astra, which many suspect is the architecture for GPT-6.
Yes, the Astra breakthroughs. This internal model autonomously solved 10 open math problems that no human being had ever cracked, including really complex problems in group theory, combinatorics, and non-SOPIC groups.
It's an incredible achievement.
It really is. But what really jumped out to me wasn't just the sheer intelligence required to solve them. It was the price tag.
The economics are what make this a historic inflection point. Based on API rates, the estimated total compute cost to discover those 10 mathematical breakthroughs was only $2,000.
$2,000 to solve problems that have stumped human mathematicians for decades.
Think about how that fundamentally alters the landscape of discovery. Historically, a monumental scientific breakthrough required decades of specialized human education, millions of dollars in university grants, and years of manual trial and error.
A lifetime of work, really.
Yes, and we have now crossed a threshold where the cost of generating a historic mathematical discovery is cheaper than a used car. The economic barrier to advanced research has essentially been obliterated.
That is genuinely staggering to think about. But it does bring up a very practical problem.
Which is?
Well, if we are letting these agents loose, like Quen coding for 16 days straight, or Astra grinding away at complex math theories for hours, how do we keep them in check? Because anyone who has used an AI knows that if a conversation goes on too long, the AI's context history gets overloaded.
Oh, absolutely.
It drowns in its own generated text, forgets its original goal, repeats work, or just starts wildly hallucinating. How does an AI run for 2 weeks without losing its mind?
Managing context windows is arguably the biggest engineering challenge in autonomous AI right now. As the AI generates thousands of lines of code or complex mathematical proofs, its short-term memory fills up.
And then it just breaks down.
Right. When it can't remember the beginning of its own thought process, the entire workflow collapses.
So one of the most fascinating solutions I saw for this is called the Long Horizon Harness.
Yes, a brilliant architectural solution.
Instead of relying on a single AI to remember everything, it splits the workflow into 3 distinct compartmentalized roles. The manager, the executor, and the auditor.
By dividing the labor, the system actively prevents the context window from ever overflowing.
It's essentially a digital construction site. Like, you wouldn't just hand a single builder a massive blueprint for a skyscraper and walk away for a month. That would result in total chaos.
Exactly.
You need the foreman, that's the manager, who looks at the master blueprint and assigns today's specific task based only on what has already been verified as completed.
Right.
Then you hand that single daily task to the builder, the executor. And here's the crucial part. The executor gets a totally fresh context window.
Yes, a blank slate.
It doesn't need to know about the plumbing installed last week. It just needs a clean slate to swing the hammer and do today's work. Finally, before the walls are closed up, the city inspector, the auditor, comes in to independently verify and sign off on the work. Only the verified, completed work gets saved back to the manager's master plan for the next day.
The beauty of that construction site setup is that the executor never gets confused by the past 2 weeks of work because its memory is deliberately wiped clean for every new task. It only focuses on the immediate problem.
And it actually works in practice, right?
The results of the Long Horizon harness validate this approach entirely. Applying this specific harness to Quinn 3.7 boosted its Weave Bench coding score by nearly 29%.
Wow.
And in another complex benchmark called Terminal Bench, using this harness actually resulted in higher scores while using fewer total tokens because the AI wasn't wasting compute power constantly rereading its own massive history.
It proves that you don't always need a bigger brain. Sometimes you just need a much smarter workflow, which provides a really interesting contrast to Meta's quiet release of MusePark 1.2.
Yes, a very different philosophy there.
Definitely. This is a multimodal model designed for long software projects, and it took the exact opposite approach by featuring a massive 1 million token context window. Now, just to be completely impartial here and report the data we have, Meta claimed on their self-reported benchmarks that MusePark 1.2 beat out top-tier models like Opus 5.
But there's a caveat to those claims.
Right. Independent analysts pointed out these claims were highly misleading. Meta chose to compare their new model against a weaker, older version of GPT 5.6 Tera, instead of the current flagship Sol model.
A classic benchmark cherry-picking scenario.
Yeah. And when you look at independent leaderboards, MusePark 1.2 actually places way behind models like Quinn 3.8 and Kimi 3, and it doesn't even crack the top 10. Though to be fair to Meta, it is highly cost-efficient compared to those larger models.
The MusePark release underscores exactly what the Long Horizon harness proved, though. Meta essentially threw a massive 1 million token memory bank at the problem, hoping sheer size and brute force memory would win out.
But the benchmarks tell a different story.
Exactly. The independent benchmarks show that just giving an AI a larger context window doesn't magically make it smarter. The future of autonomous AI isn't about building models that can hold 1 million tokens at once. It's about building intelligent architectural workflows that prevent the AI from ever needing to hold that much information in the first place.
Well, we have covered a massive amount of ground today for you. We started with a highly efficient 5 megabyte AI orchestrating symphonies, moved to coarse data weather models deliberately ignoring microscopic details to simulate 1,000 futures and save lives, and finally explored how autonomous AI agents are coding for weeks on end by policing each other's work on a digital construction site.
The through line is coordination. But I want to leave you with one final thought to mull over, building on the economics of that $2,000 math breakthrough from OpenAI.
Yeah, that was wild.
It is. So if autonomous AI can now generate, test, and mathematically verify fundamental scientific breakthroughs while we sleep, we are rapidly approaching a societal bottleneck. Very soon, AI will be capable of inventing solutions and discovering new physical laws faster than human scientists can peer review them, let alone safely implement them.
Wow.
The question we have to ask ourselves is, how will our institutions and our society adapt when the sheer speed of scientific discovery fundamentally outpaces the speed of human comprehension?
That is a heavy but incredibly important question to sit with as we watch these tools evolve, and a perfect place to wrap up this deep dive. Thank you so much for joining us and exploring all of this today. Until next time, keep your curiosity alive and maybe sleep with one eye open, because you never know what the AI is going to invent by tomorrow morning.